The pumping theorem for context-free grammars can be used like the pumping theorem for regular languages. We can use it to prove a language is not a context-free language. Before we do that, let's see how it works with languages that are context-free. So let's show that the pumping theorem applies to the language of balanced sets of left and right parentheses. So let's consider any valid string in the language, for example, a whole bunch of left parentheses followed by a whole bunch of right parentheses. We can break this up into a central section, two wings, and an outer section. If we repeat the wings W, Z, we get another string in the language. Likewise, we can show that the pumping theorem applies to the language of palindromes. So suppose we have a string in our language of palindromes. Then the first K symbols are going to be the reverse of the last K symbols, and we could break it up, again, as the beginning, the end, two wings, and a middle. And we could replicate the wings as many times as we want to, and this will also give us a string in our language of palindromes. Now that we have some idea of how the pumping theorem works, let's see where it fails. So let L be the language where we have some number of A's, followed by the same number of B's, and the same number of C's, and let's prove this is not a context-free grammar. So remember, concrete never hurts. Suppose we have a string like this. We can try to break it into a center and two wings, but if our wings include different terminals, pumping will not give us a string in the language. For example, if we break it up this way, we can't repeat W and Z because that'll put a bunch of B's in the middle of all of our A's, whereas the strings in our language have to consist of A's followed by B's followed by C's. Now, the important thing to remember is that our concrete example isn't a proof. Maybe we just weren't clever enough to find the right string. So now we can move on to the proof. Suppose that a string in our language can be broken down this way. So if W includes A's, B's, and C's, it must necessarily have the form some number of A's, followed by all of the B's, followed by some number of C's. And this means U, Z, and Y can only include the C's. This means that if we try to compose x w squared u z squared y, we get x, remember that's some number of a's, followed by our w, followed by our w again, followed by the remaining portion, which must consist entirely of c's. But remember, the strings in our language consist of a's, followed by b's, followed by c's, and we don't get this mixing that we see here, so this is not a string in our language. So whatever w is, it can't include a's, b's, and c's. Similarly, if w includes a's and b's only, then xw squared will include some b's between the a's. So that'll be whatever x is, followed by w again, and again this can't be a string in the language. This means any possible w must consist of repetitions of a single terminal. So what if w is just a bunch of a's? So now consider our pumped string. This string has I more a's than our original because we've added this w string. If it's in our language, then it must also have I more b's and I more c's. But the only difference is this additional string z. And so if w is I a's, then z is I b's followed by I c's. And consequently, x w squared u z squared is whatever x is, followed by w, again, the middle portion, z, again, and whatever the last portion is. But again, because this string mixes up the B's and C's, this string isn't in our language. And if W consists of B's only, or if W consists of C's only, we run into a similar problem. You should prove that. Consequently, it's not possible to write AN, BN, CN as a string where we can apply the pumping lemma, and what this means is that no context-free grammar could be found for this language. So what does this mean? We found that finite automata could process regular languages, but there are languages that are not regular, like the language of palindromes. To deal with these languages, we created pushdown automata, and pushdown automata could process context-free languages, but there are languages that are not context-free. To process these languages, we need a new approach, and we'll take a look at that next.